Thank you, Takwai. It's really a pleasure to open up this important conference, and I'm very honored that you invited me to do that. So this morning, I would like to tell you something about how I view learning and thinking in CSCL groups. This may be a little different from how you have viewed learning and thinking before, so I hope it will be challenging and stimulating for you, and maybe a little controversial. The field of CSCL is particularly interested in the way that small groups can build knowledge together thanks to communication and support from networking technology. I hope that CSCL environments can be designed that make possible and encourage groups to think and learn collaboratively. In my research, my colleagues and I look at logs of student groups chatting and drawing about mathematics in order to see if they build on each other's ideas to achieve more than they would individually. I wonder how they understand each other and build shared language and a joint problem focus, what kinds of problems of understanding they run into, and how they overcome these. How do they accomplish intersubjective meaning-making, interpersonal trains of thought, shared understandings of diagrams, joint problem conceptualizations, common references, and coordination of problem-solving efforts? What can we say about the general methods that small groups use to learn and think as groups? How can we support and encourage this better with software support for social awareness, social networking, simulations, visualizations, communication, with pedagogical scaffolds and guidance, with training and mentoring, with access to digital resources, with new theories of learning and thinking? To answer these important questions, we must look carefully, I want to argue, at the details of discourse in CSCL groups and develop innovative tools and theories. About 2,600 years ago, Confucius viewed learning and thinking as belonging together. The learning sciences of the 21st century agree with this. They view learning as involving meaning-making by the learners. Students who just passively accept instruction without thinking about it and coming to understand it in their own way of making sense of things will be wasting everyone's time. Why? Because they will not be able to use the new knowledge or to explain it. Of course, someone can learn something one day and make sense of it later when they try to use it in different circumstances and to explain their use to other people and to themselves. But if they never integrate what they have learned into their own thinking and acting, by applying it where appropriate and talking about it clearly, then they will not have learned anything important. What we as learning scientists have learned in recent decades in the West is influenced by what philosophers before us said. For instance, most Western philosophers, until the middle of the 1900s, thought that knowledge could be expressed by propositions, sentences, or explicit statements. If that is true, then the learning of knowledge can consist simply of students hearing or reading the right sentences and remembering them. But Ludwig Wittgenstein's book, Philosophical Investigations, published in 1953, questioned this whole view of learning and thinking. It looked at math as a prime example. Mathematical knowledge can be seen as a set of procedures, algorithms, or rules. But Wittgenstein asked how one can learn to follow a mathematical rule. For instance, if someone shows you how to count by fours, saying 4, 8, 12, 16, how do you know how to go on in that series? Is there a rule for applying the rule of counting by fours, such as take the last number and add 4 to it? And if there is, how do you learn that rule? By another rule? Eventually, you need to know how to do something that is not based on following a propositional rule, like counting, naming numbers, recognizing what numbers are larger. The use of explicit rules must be somehow grounded in other kinds of knowledge. These other kinds include the tacit knowledge of how to behave as a human being in our culture, how to speak, count, ask questions, generalize, put different ideas together, apply knowledge from one situation in another context, and so on. Wittgenstein's question brought the logical view of knowledge as explicit propositions into a paradox. If knowledge involves knowing rules, then it must involve knowing how to use rules, which is itself not a rule. Wittgenstein was an unusual philosopher because he said that problems like this one cannot be solved by contemplation, but rather by looking at how people actually do things. He said, "Don't think, look." I try to follow Wittgenstein's advice. I try to view how people actually do things. Rather than telling you what my views or ideas are about learning and thinking in CSCL groups, I want to show you how I view or observe learning and thinking in CSCL groups. The term view in the title of my talk has this double meaning. It means both viewing by looking at something with my eyes and also viewing in the metaphorical sense of thinking about something from a conceptual perspective. The Greek philosopher Plato, who lived at about the same time as Confucius, made this metaphor of viewing popular in Western thought. Although Wittgenstein did not himself actually look at empirical examples of how people follow rules in math, we can. By carefully setting up a CSCL session, we can produce data that allows us to view small groups of students learning how to follow math rules and thinking about the math rules. This is what I do to view learning and thinking in CSCL groups. It is the basic approach of the science of group cognition that I want to describe today. The work of my research team and other colleagues involves looking closely at some rich examples of student groups learning and thinking about math. I'd like to share a brief excerpt from one of these examples with you and talk about how we go about viewing the learning and thinking in this group of students. So today I'll be talking about an online event that occurred 3.5 years ago, but we can still view their learning and thinking in the log of their interaction. 3 students who were probably about 16 years old at the time met with a facilitator in an online chat environment on 4 days in May 2006 for about an hour in the late afternoon each day. The participants were distributed across 3 time zones in the US. The event was part of the virtual math team's research project of the online math forum. The topic for this event was to explore a pattern of sticks forming a stair-step arrangement of squares, as you can see there. The VMT, or virtual math team's online environment, consisted primarily of a synchronous chat window and a shared whiteboard. At the end of each session, the students were supposed to post their findings on a wiki shared with other teams participating in the Spring Fest. Between sessions, the facilitator posted feedback to the students in a text box on the whiteboard. Today I want to look at an excerpt from the end of their 3rd session. The 3 students had already solved the original problem up here of the stair-step pattern of squares. They had also made up their own problem involving 3-dimensional pyramids. Now they turned to look at the problem that another team, Team C, had described on the wiki after session 2. So Team B is looking at an algebraic expression that the other team of students had derived for a diamond pattern of squares. They start to draw the pattern in their whiteboard down at the bottom there. And they chat on the side here as a team about the problem of this new pattern. One of the students, named Asinx, makes a proposal on how to look at their problem. First, he announces that he has an interesting way to look at it. And the arrow there is pointing, I don't know if you can read it, but it says, I have an interesting way of looking at this problem. Note that he uses the word look in the same double meaning that I do in my talk title. As we will see, he means he has a new way to think about the problem mathematically, and that involves a way of observing a visual image of the problem. The group does its thinking both by typing text and algebraic expressions in the chat window, and by simultaneously drawing and viewing diagrams or geometric constructions of the problem in the shared whiteboard. Asink's announcement opens an opportunity for the group to discuss a way of looking at the problem that Asink's would like to share with the group. In fact, the group takes up Asink's offer, and the students spend the next 8 minutes trying to each understand it. As it turns out, they will work on Asink's view of the problem for the rest of this session and most of their final session. A VMT chat session can generally be analyzed as a series of themes or discussion topics. Often themes come and go, and different themes overlap, with one wrapping up while another starts up. Researchers can identify the boundaries of a theme when a new theme opens and an old one closes. In this case, the group has been talking about how the diamond pattern grows as a geometric figure for a couple of minutes, and then they discuss Team C's algebraic expression for a couple of minutes. As these themes get played out and there's a pause in the chat, Asink's makes a move to open a new theme for the group. And here's a log of part of their chat. Asink's announcement that he has an idea to share with the group, in his first statement here, I have an interesting way to look at this problem, is a way of introducing a new theme. Conversations often flow by new contributions picking up on something that was already being discussed. Online text chat tends to be more open than face-to-face talking. Chat does not follow the strict turn-taking rules of conversation. However, it is still common to do some extra work to change themes, even in chat. In a sense, Asink's is asking permission from the group to start a new theme. Quicksilver responds encouragingly right away by saying, "Tell us." Actually, Asink's already starts typing his proposal before he gets Quicksilver's response, but it is not posted until afterwards. His proposal is, "Can you see how it fits inside a square?" Here he structures his proposal as a question in order to elicit a response from the other members of the team. Note that he uses the term see in his proposal with the same double meaning as the term view in his prior announcement. As we shall see in both senses, the group tries to work out and comprehend Asink's proposal both conceptually and visually. Both Bwang and Quicksilver respond to Asink's proposal with yes. However, both modify this response. Bwang starts to type something else, but erases it. Then he posts two messages, "Oh" and "yes." This indicates that he did not immediately understand the proposal fully, but it took him a couple of steps over a few seconds. Quicksilver follows his initial positive response with, "You are saying the extra spaces?" He is looking for more clarification of the proposal. While Quicksilver is typing his request for clarification, Asink's is typing an expansion of his initial proposal. Also, do you see if you add up the missing areas? The analysis of interaction moves is central to the science of group cognition. This is the level of granularity of many typical group cognitive actions. In this case, the action taking place is the opening of a new theme, one which will provide direction for the rest of this group's event together. This move is an example of one way in which a group can establish a shared understanding of a diagram or select a joint problem conceptualization, depending on how we understand the terms look and see. Other moves that we often see in VMT logs are defining shared references, coordinating problem-solving efforts, planning, deducing, designing, describing, solving, explaining, defining, generalizing, representing, remembering, and reflecting as a group. In conversation analysis, one typically looks for so-called adjacency pairs. A prototypical adjacency pair is question and answer. Azink's offering of a question, "Can you see how it fits inside a square?" followed by Bwang and Quicksilver's response, "Yes, yes," illustrates the structure for the simplest case. One person poses a yes-no question and the others respond with an affirmative answer. Response structures are often more complicated than this. Text chat differs from talk in that people can be typing comments at the same time. They do not have to take turns and wait until one person stops talking and relinquishes the floor. They will not miss what the other person is saying because, unlike with talk, the message remains observable for a while. The disadvantage is that one does not observe how people put together their messages with pauses, restarts, corrections, visual cues, intonations, and personal characteristics. Because the sequencing in online chat texting is less tightly controlled than in face-to-face talk, response pairs are likely to become entangled in the longer sequences of group moves. This may result in the common problem called chat confusion. It can also complicate the job of the researcher. In particular, it makes the task of automated analysis more complicated. In convoluted chat logs, it is essential to work out the response structure, or threading, before trying to determine the meaning making. The meaning making still involves participants interacting through the construction of response pairs, but in chat, people have to recreate the ties among these pairs. Realizing this, the group members design their postings to be read in ways that make the response pair or threading structure apparent, as we will see. In his posting, "Can you see how it fits inside a square?" Azink is comparing the relatively complicated diamond shape in blue there to a simple square in red. This is a nice strategy for solving the group's problem. The group can easily compute the number of stick squares that fill a large square area. At the same time, Azink poses his proposal in visual or graphical terms as one of seeing how one shape fits inside of another. The group has been looking at diagrams of squares in different patterns, both the drawing by Team C in their wiki posting and Team B's own drawings in their whiteboard. So Azink seems to be visualizing a possible modification to one of the diamond drawings, enclosing it in a square figure. He is asking the others if they can visualize this also, so that the group can use this to simplify and solve their problem with the diamond. Azink presents his proposal about rethinking the problem as a question about visualizing the diagram. The group has been working in the VMT environment, going back and forth between text in the chat and drawings in the whiteboard. They have started with problems presented graphically and have discussed these graphical problems in their text chat. They have shared different ways of viewing the relationships within the drawings, and they have gradually developed symbolic algebraic ways of expressing general relationships about patterns in these drawings, working out these symbolic expressions in the chat, and then storing them more persistently in the whiteboard. So I've been calling Azink's chat posting a problem-solving math proposal. However, it is presented in the grammatical form of a question. Azink did not simply state a proposal like, "I think we should enclose the diamond in a square, calculate the size of the square, and then subtract the missing areas." Rather, he first announced that he had, quote, "an interesting way to look at this problem," end quote, and then explained his way of looking by asking if the others could, quote, "see how it fits inside a square," end quote. Presenting a proposal calls on the others to accept the proposal and start to work on it. Of course, the others can reject the proposal, ask for clarification about it, make a counter-proposal, or ignore the proposal. But Asings is apparently not ready to formulate a full proposal and have the others accept or reject it. So he takes another preliminary step. He asks them if they can visualize something. He puts this to them as a question. If they say yes, then he can proceed to make his proposal, or perhaps the others will see the implications of his interesting way to look at the problem and propose the strategy without Asings having to advocate it, explain it, and defend it. If they say no, then they cannot see how it fits inside a square, then he can explain his view further so they will be better prepared to accept his proposal. Asings's question is ambiguous at a purely syntactic level. He asks the others, can you see how it fits inside a square? What does the term it refer to? People use pronouns like it rather than lengthy explicit noun phrases when the reference is clear from the context. This makes the utterance situated in its context. Its meaning cannot be gathered from the utterance considered in isolation. Often, it will reference something that was recently referred to in a previous contribution that the new utterance is building on. For instance, it could refer to something mentioned in Asings's previous utterance, I have an interesting way to look at this problem. But to say that it refers to this problem does not make complete sense. The problem does not fit inside a square. However, a minute earlier, when the group was discussing Team C's equations, Asings said about part of an equation, the 3n has to do with the growing outer layer of the pattern, I think. He was referencing different aspects of the growth of the diamond pattern, particularly its outer layer. So when he announces that he has an interesting way to view the problem, it is reasonable to assume that his new way of looking may be closely related to the observation that he had just reported about the outer layer of the diamond pattern. Because everyone in the group was following the flow of the discussion, Asings could refer to the topic of the outer layer of the diamond pattern in the shorthand of the pronoun it. When he typed, can you see how it fits inside a square, he could assume that the readers of this posting would understand that he was referring to how some aspect of the diamond pattern can be seen as fitting inside of some square shape. Although the reference to some aspect of the diamond pattern is relatively clear, the details are not clear about just what aspect of the diamond is to be visualized or focused on visually, where a square is to be constructed, and how the diamond fits inside the square. At this point, only a rather confusing image of a diamond pattern is visible on the whiteboard. Bwang and Quicksilver both respond initially to Asings's question with yes. However, as we saw, Bwang indicates some hesitancy in his response, and Quicksilver asks for further clarification. Asings and Quicksilver discuss what they see when they fit a diamond pattern inside a square. Quicksilver notes that the extra spaces, which are colored red in that diagram, look similar to the stair-step pattern that the team worked on previously. But Asings goes on to talk about the 4 squares on the outer layers, on the outer areas of the square, confusing Quicksilver. That is, as they each try to work out the details of Asings's view, they realize that they're not seeing things quite the same way. Quicksilver suggests that Asings show what he means on the whiteboard so the ambiguity of his proposal can be resolved. Rather than drawing it himself, Asings asks Bwang to do a drawing. Bwang draws a very clear diagram on the whiteboard for the diamond pattern when n equals 2, which is the diagram down there in red and white. As soon as Bwang completes his drawing, he makes explicit the problem-solving proposal that is implicit in Asings's way of viewing the problem or the pattern. We just have to find the whole square and minus the 4 corners, he says. His drawing has made this process very visible. He drew the diamond pattern with white squares, and then filled in a large square that the diamond fits into by adding the red squares. The red squares fill in symmetrical spaces in the four corners of the diamond pattern. The group then discusses the view of the diamond pattern fitting into an enclosing square. They eventually realize that some of their observations are only true for the diamond pattern at a certain stage, where n equals 2. So Boeing then draws the pattern for n equals 3, this larger white diamond. Here it starts to become visible that the red squares in each corner follow the stair-step pattern from their first session. The group has realized that viewing a graphical image of a mathematical pattern can be very helpful in thinking about the pattern. However, the image captures just one particular stage in the pattern, one value of n. They then start to look at images for different values of n, or different stages in the growing pattern. They count the number of red squares in a corner as n increases, and notice that it goes 0, 1, 3, 6. This pattern is familiar to them from their earlier analysis of the stair-step pattern. They call this sequence triangular numbers from Pascal's triangle, which is often useful in combinatorics math problems. They know that this sequence can be generated by Gauss's formula for the sum of the consecutive integers from 1 to n. Unfortunately, at that point, Boeing has to leave the group, but when they return in session 4, they will quickly put together the simple formula for the enclosing square minus this formula for the number of squares in each of the four corners to solve their math problem. Let me pause now from all these details about the case study of 3 students in a virtual math team session and talk about how I view learning and thinking in CSCL groups. I've tried to demonstrate that I view learning and thinking in CSCL groups by viewing with you how a group of 3 students thought and learned collaboratively within an online environment for drawing and chatting about mathematics. I took you through several levels of analysis of the group discourse, and then the levels are listed on the slide. We started by mentioning the overall context of the event. This was an online event in which Team B, consisting of 3 students, met in the virtual math team's environment to discuss patterns of squares formed by sticks. We then focused on the smaller session unit, looking at Team B's 3rd session, in which they considered a pattern that another group, Team C, had analyzed. Within this session, we identified one of several themes of discussion in that session, namely the one involving Azink's posting, an interesting way to look at this problem. Azink introduced the theme by initiating a group-solving move. Namely, he got the group to view the problem in a certain way, as a diamond enclosed in a square. We saw how the group ended up drawing images in their shared whiteboard of diamond patterns enclosed in squares. Azink introduced this group move in a subtle way. He did not simply come out and say, "We should analyze this pattern as partially filling an enclosing square." Rather, he first announced that he had an interesting view, and then he asked if the others could view the problem in a certain way. He did this through a question-answer response pair. He asked a question which elicited a yes or no response from the others. By eliciting the response, he oriented the others to looking at the diagram in the whiteboard in a certain way, namely in the way that he was proposing. Azink's formulation of his question looks like a simple utterance in question format, but it entails selection from a number of different ways of picturing the relationships among the diamond pattern, the enclosing square, and the empty corners. To begin with, one must decide what the reference to it is doing. References like the pronoun it are frequent and unavoidable in online text chat. They require the reader to understand or reconstruct the implicit threading or response structure of the chat. The difficulty of doing this often leads to confusions, which require the participants to spend time clarifying the content and structure of their discussion. For instance, in our example of the move of seeing the diamond in the square, the group had to engage in a couple minutes of chatting and drawing to co-construct a shared understanding of the problem. In other words, in order to view learning and thinking in CSCL groups, I do not try to figure out what is going on in the heads of the students. Rather, I try to figure out what is going on in their chat postings and their drawing actions. This is what I call the group's interaction. In VMT, the interaction of the virtual math team consists of sequences of chat postings and drawing actions. My first step in figuring out what is going on in the chat postings and drawing actions is generally to analyze the sequencing of these by reconstructing their response structure, what previous action each new action is responding to, and what kind of actions it is eliciting, what it is opening up as an interaction space for, or what kinds of responses it is making relevant as next postings. Often this leads to some kind of threading diagram, uptake graph, or interaction model. This provides a basic structure of the meaning-making sequencing. Then I try to understand what problem-solving work is being accomplished at each point in the sequence. This involves looking at different levels of granularity, such as the event, session, theme, move, pair, utterance, and reference. Understanding the meaning that the group is co-constructing in their interaction generally involves going back and forth through these different levels and integrating partial interpretations from the different levels. Through this process, I can gradually view the learning and thinking that takes place in the CSCL group. This learning and thinking is not something that takes place primarily in the minds of the individual participants. Although the individuals in the group are each continuously understanding in some way what is going on and responding to it with their postings and drawings. Rather, when there is an intense collaborative process taking place in the online environment, the thinking and learning takes place in the visible text and graphical interactions. In a CSCL collaborative interaction, thinking does not take place the way we usually think of thinking. Thought or cognitive processes do not take place by neurons connecting and firing in a brain. They take place by text postings and drawings referring to each other and building on each other. We will look more at how this takes place in a minute. Similarly, learning does not take place the way we learned about learning. It is not a change in the amount of knowledge stored in a brain. Rather, it is a matter of knowledge artifacts being gradually refined through sequences of text postings and graphical drawings that are interrelated and that explicate each other. The knowledge artifacts may be statements about a problem the group is working on, as viewed from a new perspective that the group has developed. The knowledge artifact might be a drawing, like Wang's, or an algebraic formula that sums up the group's analysis of pattern growth. Rather than talking about learning and thinking in the abstract, let us unpack some more how learning and thinking take place in Team B's interaction, in their text chatting and drawing together. So, let's go back through the hierarchy of levels of analysis in the opposite order to say something about how references, utterances, response pairs, moves, themes, sessions, and events can contribute to learning and thinking in CSCL groups. When one studies logs of virtual math teams, one sees that they spend a lot of time reaching shared understanding about references in their postings. My conference paper later this week reviews an example of this from Team B's session 4, where Azinks, Quicksilver, and Boang get quite confused about references from the chat to different equations written on the whiteboard. The reason that people devote so much time and energy to resolving confusing references is that the network of references that they build up together plays an extremely important role in their group learning and thinking. In the theory of CSCL, there's considerable emphasis on the idea of common ground and joint problem space. A group establishes common ground largely by reaching a shared understanding of how references work in their discourse. As it interacts over time, a group co-constructs a network of references that can become quite complex. As a group builds up its network of shared references, it can use more shortcut references to point to things without creating confusion. People can use deictic references to point to things in the network, like this formula, the second equation, or it. In linguistic terms, the shared network of references provides a background for referring to things. In problem-solving terms, the network of references forms a joint problem space, a shared view of the topic that the group is addressing. For Team B, the joint problem space starts with the stair-step pattern and the chart of the number of sticks and squares for each stage of this pattern, as presented in the topic description. By the middle of session 3, it includes the diamond pattern and the view of it enclosed in a square, forming empty corners. It also includes triangular numbers and their associated formula, as well as several other equations from Team C and from Team B's own work. The team's interaction, the text postings and drawings, gradually creates this joint problem space and is situated within it. The work and utterances of the team can only be understood by the participants, as well as by us as researchers, through an ongoing understanding of the joint problem space as a network of meaningful references. While both the students who participate in the sessions and the researchers who analyze the logs need to understand the network of references, they understand them in very different ways. The students understand how to respond to what is going on the way they might understand how to ride a bicycle down a hillside. That is, they are not reasoning about it explicitly, rationally, logically, or consciously. Rather, they are paying attention to what is going on and responding knowingly and intuitively. Quicksilver has not carried out the kind of analysis of Azink's word it the way I did, yet he could respond to it with a sophisticated set of questions. He only had a couple seconds to respond, whereas I could spend hours going back and forth over the log, arguing about explicit interpretations. People are incredibly skilled at using language without thinking about how they do it. In fact, even researchers are only aware of a small percentage of what people take into account almost instantaneously without being aware of it. We say that Azink designs his announcement and proposal so that it will be read by Bwang and Quicksilver in a way that will lead them to understand in a complex way. They will figure out what it is referencing, but also realize some of the ambiguity of the reference. They will also come to think about the strategy for finding the number of squares in the diamond pattern because of this ambiguity. But Azink does not design his statement explicitly through a rational sequence of logical arguments. Rather, as a skilled user of language, he gives voice to a well-designed posting that responds to the current discourse situation. It is somewhat like the way a skilled off-road biker responds to the terrain intuitively as she is speeding down a rough hillside with no time to think about what she is doing, and she somehow designs an optimal path for her journey. An important aspect of the design of utterances or postings is how they are designed to fit into what comes before and after them. The clearest and simplest example of this is the adjacency pair or response pair, such as a question-answer pair. A question elicits an answer. That is, stating a question projects that an answer will be given in response. It opens a conversational space for an answer. It makes it relevant for the next utterance to be an answer, responding to the question. In other words, a question is designed to be read as something that should be responded to with an answer. A question worded like, "Can you see how it fits inside a square?" is designed to be answered with a yes or a no. The question and answer pair forms a unity, a small unit of interaction between people. The yes response shows that the posting it is responding to was read as a question and creates the pair as a successful question-answer interaction. One of my first discoveries in studying virtual math teams was that math discourse is largely driven forward by what I called math proposal response pairs. These have the following structure. First, an individual makes a bid for a proposal to the group suggesting how the group should continue to do its mathematical work. And second, another member of the group accepts or rejects the proposal on behalf of the group. This is the simple default form of the math proposal response pair. If the proposal is accepted, then work begins on the proposal, often in the form of a follow-up proposal. Of course, there are many variations and complications possible. The bid can be ignored or never responded to. In that case, it does not function as an effective proposal. At best, it is a failed proposal. Before a proposal response is made, there can be other response pairs inserted in the middle of the expected pair, such as a clarification question. It is also possible that someone will propose an amendment to the proposal bid before the original is accepted. Thus, a simple pair can develop a complicated recursive structure of insertions, extensions, repairs, etc., with each of these being subject to their own insertions, extensions, or repairs. Eventually, each of the intervening pairs may get closed with its anticipated response, and then the original pair may be completed. Group problem-solving moves often have the structure of a longer sequence than a simple pair. Such a longer sequence may consist of a complex of response pairs embedded in one another. To identify such a structure, it may be necessary to first conduct a threading analysis to determine what is responding primarily to what. Then it is often useful to see how this longer response sequence is built up out of simple response pairs. Together, these intertwining response pairs form a successful move, introducing a new theme for the group. As an example, let's look again at Asinx's move in this chat excerpt. We can see 4 response pairs here. First, Asinx announces, "I have an interesting way to look at this problem," and Quicksilver responds by asking him to tell us. Second, Asinx asks, "Can you see how it fits inside a square?" And first Wang responds yes, then Quicksilver responds yes, then Wang responds again, more emphatically, "Oh, yes." Third, Quicksilver asks a clarification question about the proposal implicit in Asinx's question. "You are saying the extra spaces?" And fourth, Asinx, in parallel with Quicksilver's question, asks a follow-up question which contains an implicit further proposal about the group's work. Also, do you see if you add up the missing areas? As the discussion continues, Quicksilver responds to Asinx's question, and the two of them continue to discuss the issues raised in both their questions. Asinx's move introduces the theme of the diagonal pattern viewed as enclosed in a square with missing spaces in the 4 corners. As we have just seen, the move consists of multiple response pairs that drive the work of the group to consider this theme. As the theme evolves, the group draws and discusses some increasingly elaborate drawings to view the patterns that the theme involves. The group considers different stages of the pattern for n equals 1, 2, 3, 4, and how the number of missing spaces changes as the diamond pattern grows. This leads them right to the point where they can formulate an equation to summarize their analysis of the pattern growth. Unfortunately, Wang has to leave the session, and they do not complete this work. During the 4th session, 2 days later, the group picks up this theme and discusses it repeatedly, eventually deriving the equations for number of squares and sticks in the diamond pattern at all stages. This theme is the basis for the equation for number of squares, which simply subtracts the number of missing spaces in the four corners of a square that encloses the diamond pattern. After Wang left the third session, Asings and Quicksilver try to review the group's accomplishments. They become confused about various equations and unsure of their ability to explain what the group has figured out. They end the session with Quicksilver saying, "Then let's pick it up next time when Wang can explain it." This ends one session and projects what will happen in a future session. At the beginning of this event, the students were not part of a particularly effective group or team. They did not build much on each other's contributions and were hesitant to make proposals, ask each other to undertake tasks, produce permanent drawings, or manipulate mathematical symbols. That all changed dramatically during their four-session event. By the end, they had many graphical, narrative, and symbolic representations or expressions related to their mathematical topic. They worked effectively together and solved their problems well. Problem-solving methods that one person introduced were later proposed and used by the other group members. You may be wondering now if each of the students learned mathematics. The interesting thing about looking closely at what really went on in this event is that what we can traditionally consider to be the math content actually plays a relatively minor role in the group's problem solving. Yes, it's true that content is brought in. The students talk about triangular numbers and they apply the formula for summing consecutive integers, for instance. Often this math content is brought in quickly through proposals by individuals. It is then discussed through responses to the proposal that check that everyone understands the math content and agrees on its applicability. However, the bulk of the hard work is not accessing the traditional math content, but selecting, adapting, integrating, visualizing, sharing, explaining, testing, refining, building on, and summarizing sequences of group response pairs. These proposals and discussions reference not only math content, but also various related resources that the group has co-constructed. The learning and thinking of the group takes place through the group's discourse as a temporally unfolding multi-level structure of response pairs interwoven into larger sequences of group moves, problem-solving themes, and sessions of events. The group learns about the mathematics of its topic by building and exploring an increasingly rich joint problem space. It thinks about the mathematical relationships and patterns by following sequences of proposals, raising and responding to various kinds of questions, and engaging in other sorts of interactional moves. Some of this gets summarized in persistent knowledge artifacts like drawings, concepts, equations, solution statements, and textual arguments. The building of the joint problem space generally requires a lot of work to resolve references and to co-construct a shared network of meaning. The math skills, like following certain procedures to do long division or to transform symbols, are not where the deep learning takes place and real knowledge is involved. Rather, the ability to sustain progressive inquiry through methods of group interaction is the real goal. This ability makes use of the math skills as resources for answering questions and coming up with new proposals. If you wonder how to view learning and thinking in CSCL groups, then follow Wittgenstein's advice. Don't think, look. My colleagues and I have tried to do this by looking at the work of virtual math teams in the way I have described today. We have been amazed to discover that collaborative learning and group cognition are a lot different than people thought. Computers in education can bring many advantages, even as seen within a traditional view of education. They give students and teachers access to all the information on the web. They provide the ability to access lectures anywhere, anytime, on large scales. They can support testing, tutoring, and scripting of learning processes. They offer simulations, educational gaming, virtual reality, and artificial intelligence. But networked computers in education, using CSCL software environments like VMT, also offer opportunities for a radically new view of learning and thinking. The networking of students can let them get together with others interested in similar things around the world. Effective collaborative learning experiences help students learn how to work, think, and learn in groups. Group work is a new force of production in the world, and students need to learn how to produce knowledge in teams. CSCL events can give students firsthand, hands-on experience in knowledge building. Discussing math in peer groups teaches students how to do math, how to talk math, how to make math connections, how to learn math, and think mathematically. In this second view of computers in education, book learning of facts and rote procedures has a place, but the more important kind of learning comes through doing. CSCL groups can provide effective learning experiences in which teams of students actually do mathematics by exploring rich problem spaces and discussing them the way that Asincks, Quicksilver, and Boang did. So there are two popular approaches to CSCL theory. One is that collaborative learning can be seen as an extension of traditional individual learning. Individuals possess knowledge that they can state in sentences and can communicate to other individuals. Our common sense concepts can describe this, and we can measure what individuals know at different times. Learning in this traditional view is an increase in individual knowledge. But there's also a second approach to CSCL theory, which says that collaborative learning can be viewed as qualitatively different from traditional individual learning. And we need to discover the nature of collaborative learning and its relation to individual learning by exploratory research. We need to rethink our ideas about learning, collaboration, education, computer support, research methodology, and cognitive theory. We need to look carefully at data from real CSCL sessions to see what actually takes place there without imposing our common sense views. It should be clear by now that I view learning and thinking in CSCL groups as a mystery to be investigated, not as something well understood to be measured. It is a new form of human existence with great potential. We must observe it to learn how it works. My colleagues and I have begun to do this, as have other researchers in CSCL. I've tried to indicate to you this morning how you can go about observing learning and thinking in CSCL groups. It may be easier to understand issues of technology design and of traditional instruction when studying computers in education than to understand this new view of learning and thinking. But I believe that if we hope to get the most benefit from computers in education and to understand how groups learn and think in CSCL groups, then we will have to closely observe the discourse and interaction in ways similar to what I have presented here. And I hope we will have opportunities to discuss this further during the conference. Thank you.